In this video, we will discuss the Langevin's theory of diamagnetism. So we know that diamagnetism in the material arises due to change in the atomic orbital state induced by the applied magnetic field. So you know that when we say that, for example, here I will consider this is the plane X, Y, Z, and here we are consider the electron which is orbiting around the nucleus, and we know that the electron which is revolving in an orbit constitute an electric current. An electron revolving in an orbit constitutes an electric current. And we will consider this a motion of electron in an orbit is equivalent to the current in a closed circuit. So we will consider this case equivalent to a current in a closed electric circuit. So now when we apply the electric field, when we apply the magnetic field, or you can say the application of magnetic field, the induced, or this magnetic field induces an electric field. This applied magnetic field induces the electric field. So here we can denote it, say for example, EI. In this closed circuit, you can say, or in this closed path. And the induced EMF, which I denote with the symbol VI, under the influence of this applied magnetic field, this induced EMF will accelerate this electron in the reverse direction, to the original motion, or you can say this induced EMF deaccelerate. This EMF deaccelerate the electron motion as per Lenz's law. So you know that in Lenz's law, the real, according to Lenz's law, it will always oppose the real cause of its production. So the induced EMF, so this under the application of the applied field, magnetic field, this electron which is revolving in our orbit will get deaccelerate, and due to the induced electric field and the deacceleration of the electron, we can write the expression for deacceleration of the electron due to the induced electric field which I denote is given as, I write this deacceleration with symbol AI. This is a force EI, E charge, and E is the induced electric field divided by the mass of the electron. Okay, and we can also write the expression for this induced electric field. EI is equal to V by D. So D is here is perimeter of this orbit. D is perimeter the orbit. So if I consider that say rho is the radius of the projection of the orbit in the xy plane. So this D I can write perimeter will be equal to 2 pi rho, and here I am considering that this the rho is the projection of this this orbit in the xy plane. Okay, so and EI here I will write VI. Okay, and this EI comes out to be equal to VI by into 2 pi rho. So I will substitute the value of EI from here in this expression. So use the, say this is equation 2, this is one equation, use equation 2 in equation 1. So I will get the value of deacceleration of the electron, which is equal to EY m by 2 pi rho into VI. Okay, this is now VI is here, this is induced EMF, and the value of this induced EMF is equal to the rate of change of the flux across this circular orbit. So this VI is equal to the rate of change of magnetic flux magnetic flux across the circular orbit, which is in the xy plane. And here we will consider that the direction of applied field is normal to the xy plane, or you can say the perpendicular to the xy plane or circular orbit. Okay, so the flux through this, or magnetic flux through the circular orbit is given as, we can write this is B is the magnetic flux density into area of this circular loop. So this is B into area is, rho is the radius, so I will write B into 2 pi B into pi rho square. So this is the value of the flux linked with this circular loop. And we know that the value of this induced EMF is the rate of change of this flux. So I will write this VI is equal to minus dV by dt B pi rho square. So this is the value of induced EMF. And now I can substitute the value of Bi in this. This is equation number 3. So use this above value in equation 3. So I will get here acceleration is equal to, deceleration is equal to E by m 2 pi rho into minus, I will write dV by dt into, I will keep it out, pi rho square. So this value comes out to be equal to minus E rho by 2m into dV by dt. And for this deceleration, I can write this is equal to dV by dt. This I can write this is equal to, because this is deceleration, so this is equal to rate of change of the velocity dV by dt. So I will got, or I can write dV by dt is equal to minus E rho by 2m into dV by dt. So this is, I got the expression. And I can also rewrite it, this is dV is equal to minus E rho by 2m into dV, like this, and integrating both sides. Here we can have velocity changes from deaccelerated from v1 to v2, and the value of field changes from 0 to b. So on integrating it, I can get this expression v2 minus v1, which is equal to minus E rho by 2m into b. And I can write this is equal to delta v, which is change in the velocity, you can say change in the velocity of the electron in the orbit under the application of the magnetic field. And this change in the velocity results in an angular momentum. So we can say that this will result in an angular momentum and hence a magnetic moment is induced in this circular loop. So there is change in the velocity, and due to the change in the velocity, which results in the angular momentum, and which results, or we can say that a magnetic moment will induced. Okay, so we can now write the expression for the induced atomic magnetic moment. So we can write the relation between the induced atomic magnetic moment and the velocity. Okay, so we know that the expression for the induced magnetic moment, I will write the expression in term for the induced magnetic moment, so which is equal to current into area, and we know that current is charge per unit time into area. So here I will write the expression for the T here. So in this case, total perimeter is 2 pi rho, and I will divide it with the change in the velocity. So instead of this T, I will write this 2 pi rho by V, and we know that the area is pi rho square. Okay, area of this the circular loop. So this induced magnetic moment comes out to be E into this is 2 pi rho, here I will write change in velocity, and here pi rho square. So finally I will got here E rho will get cancel, E rho by pi also get cancelled, 2 into delta V, change in the velocity. And we know that what is the value of the change in the velocity. Earlier we have tried this expression. So we know that delta V is equal to minus E rho B by 2m. So this mu I comes out to be equal to E rho by 2 into with minus sign E rho B by 2m. So it comes out equal to minus, or I will write here minus E square rho square by 4m into B. So this is induced atomic magnetic moment. So in this equation we got that the induced magnetic moment is directly proportional to the square of the radius of the projection of the orbit in the xy plane. this is the represent the square of the projection of the orbit in the xy plane. And in the presence of magnetic field, in the presence of field, we can say the magnetic field, the plane of the orbit varies constantly with respect to the direction of the applied field. Okay, so we have to replace this rho square y and average value. Why? Because this plane of this orbit, it changes constantly with respect to the direction of the applied field. Okay, so we have to replace this with the average value, and I can write this rho square because it is in the xy plane. I can write this with average value. I will not consider here rho square, but I will consider the rho average square, and here is the x square average plus y square average. Okay, and if we consider that r square average is the average square radius of the electron orbit, then I can write r square average is equal to x square average square plus y square average square z square average. Okay, and if I consider that if we assume the atom is spherically symmetric, okay, symmetry, in that case I can write this x square average is equal to y square average, z square average, they all are equal, and I can write this, they must be equal to r square average divided by 3. So using this I can write this rho square term, average square term by, which is equal to x square average plus y square average. I can replace with 2 r square average by 3. So I can replace this rho square with this term. So now the expression for the induced atomic magnetic moment, I can write mu I is equal to minus which was minus e square rho square by 4m into rho. I can replace rho square with now here e square r square average 2 by here 2 by 4 m 3 into v. So I can write this is equal to minus e square r square average divided by 6m into v. So this is the value of induced magnetic moment. Now if I consider that in an atom there are z electrons in the atom, so what is the total induced magnetic moment in that case? Is will be, we can write this, which is equal to mu I will write now average here, mu I average is equal to z into minus e square r square average by 6m into b. So if within the atom we have Z, then this is the total induced magnetic moment. And if we consider if there are n atoms per unit volume of the material, now this is, we have written Z electron in an atom, then total induced magnetic moment will be, we multiply this induced magnetic moment with Z, because Z is now here the number of if we have Z is the Z electrons. Okay, we have, there are Z electrons in the atom, then we multiply it with Z. Okay, so if we consider that there are n atoms per unit volume of the material, then I can write the expression for the magnetization within the material is n into this term Z into minus e square r square average by 6m into v. So here we have also negative sign. So this negative sign implies that the magnetization is in the magnetization in a direction, this negative sign here in this expression, that negative, the magnetization is in a direction opposite to that of the applied field. Okay, and from here I can also write m by h is equal to, now if I write here instead of this b is equal to mu naught h, so this is m by h. From this expression I get here mu naught z e square r square ever by 6m, and this quantity we can call it diamagnetic susceptibility. Diamagnetic susceptibility. Okay, or here I have DIA, and here we got this diamagnetic susceptibility depends upon this r square. It depend upon this r square, mean square radius of the atom. Okay, and here it is independent of temperature. Now temperature. So this is regarding the Langevin theory. For the diamagnetism, here susceptibility is independent of temperature, and this susceptibility depends on the mean square radius of the atom, which is we have r square average, and it is independent of. So this is all about the Langevin's theory of diamagnetism, and this is classical theory. Okay, thank you.